Welcome back to the series of lectures on high-performance scientific computing. We will now look further into collective communication. We did the example of MPI scatter and MPI gather in the previous class. We will now look at an advanced example of the same thing. What we are now trying to look at is the MPI all gather function. Now let us see how the all gather function works. So let us say that you had 4 processes P0 to P3 and each of it had 4 distinct data elements A, B, C and D. When we do the all gather function, what essentially it does is that it gathers data from all the processes and distributes them to each and every other process. So essentially all the processes now have all the data gathered from everywhere. So if you look at it, the end result would be that P0 will have A, B, C and D, P1, P2, P3 all will have A, B, C and D. So essentially if you're looking at the way communication is going to take place in the all gather functionality is that now P0 has to receive B, C and D from 1, 2 and 3. So that makes it 3 sets of communication there. Similarly, P1 has to get A, C and D from P0, P2 and P3. So each process will have to receive 3 data members. So effectively, the total pairs of communication, if you had to do it just using send and receive, would have been 3 into 4, which is about 12 pairs. So you would have had to have 12 sends and 12 receives for this function, which is now replaced by a single line or a single function call. So this makes it very useful. But you must realize that this is a rather heavy function in the sense that when you do an all gather, it does a lot of data transfer in the background, because essentially what the MPI library does is that it will break this MPI all gather into those 12 pairs of sends and receives. Plus, the memory requirement at each node now or each process has quadrupled, or rather it will go by the total number of ranks that are there. So you have to be very careful when you use the all gather function, and you should use it only when it is necessary. Let us see a mathematical example of the all gather function. The mathematical problem that we are going to look at is vector normalization. Let us say that you have a vector of size n and we need to compute its normalized version. V norm mathematically is defined as the vector v divided by the L2 norm of the same vector. Now, the L2 norm has to be computed as a global sum, and then each component of that vector needs to be divided by this global sum. So how do we implement this using the MPI all gather approach? We assign each part of V to each process. Then each process will then compute the partial sum squares for its element. Then MPI all gather is used to share these partial results or sort of compute a global sum. Then one process will compute the global sum and then take the square root of the gathered sums. And then each process will then normalize its part of the vector. So if you think about it, the way we need to work on this problem is that first we need to take the vector v, we need to distribute it into different chunks and assign it to different processes. Each process then will compute its local sums. Then we need to do an MPI reduction sort of to capture back all these partial results, and then we need to send it back to all the processes again, so that one process computes the norm, or rather normalizes each part of its vector. So let's see how this is sort of implemented in code. I've already opened up the code over here. So again, in this example, we are hard coding it for a vector size of 8 for matters of simplicity. We can obviously make this as long as we want. We are also hard coding it for 4 processors for matters of explanation. So we have the same integers of rank and size. We now have a double vector v of n. Then each process has a local vector v, which is n divided by 4, which is the local vector segment. Then we have the local sum and the global sum. We also need to have the norm at this point of time. And then we need to have the gathered sums again, which is assuming the 4 processes. So we will initialize the MPI environment again. We will put the rank, we will take the size. We will again say what are the total number of elements per processor. So hopefully n is perfectly divisible by size. This makes life easy. Otherwise, we'll have to introduce a little bit of complicated code over here to see to it that all processors get integer number of elements and all the elements sum up to the global sum of elements. We will now initialize the vector v. So we have initialized the vector v, and that initialization is taking place only on the root process 0. We say v of I, or the ith component starting from 0 is I plus 1. So let's say our vector is 8 long, the first component of the vector is 1, the second component of the vector is 2, so on and so forth till 8. We will then scatter the vector v to all processors. So essentially what we are doing is we are taking v, we are saying that please give 2 elements per processor. This time we are saying it's MPI double, the data type is MPI double. In the last example it was an MPI integer, but we are saying the vector is a double over here. So essentially what we are saying is that we are sending larger bits of memory to these processors. And then they are to be stored in the local vector, and they are also too long, and again the receipt is an MPI double. And the information is coming from 0. So once this is done, we have now we go ahead and compute the local sum. So we have computed the local sum by doing Vi into Vi. Here we are now gathering all the partial sums using the MPI all gather function, right? So what we are doing is we are taking the local sum and we are sending it to gathered sums using the all gather function. So that means every process will now have, essentially you're gathering the local sum from all the processes into one particular process. So we are putting this over here. Now if you're rank 0, I'm going to go and compute what is the global sum, and then I'm going to compute the norm from there by taking the square root of the global sum, which is essentially doing the mathematical operation being shown in the second equation over here. We then once we compute the norm, we now have to send it to each and every process. So we are now using the broadcast function to send it to each and every process, and since only rank 0 had computed the norm, rank 0 will do the broadcast from here. And finally, we will then go and normalize each part of the vector. So every individual process will normalize its individual part by dividing it by the value of the norm. And finally, we gather the normalized vector at the root. So we gather back all the local v's and we put it into the root. We then put out what the normalized vector is, what are the components of the normalized vector over here. And in this case, we are using it up to 3 decimal accuracy. Let us now see how we can compile this program and execute it. We will now say MPI CC minus standard C99 vector norm dot C minus output vector norm. Since we are using the math function square root, we also need to link it to the math libraries, and for that we need to pass an additional flag minus LM. So we need to link this math library since the square root function is a special function. So once we compile this, we will have an executable, and we should be able to run using MPI run minus NP 4. Remember, we have hard coded this for 4. We will say vector norm, and then we get the answer for the vector norm. If we run it with some other number of processors, you'll see that we are going to get some sort of incorrect answers. This is simply because, again, we have hard coded it to 4 processors. And to make it sort of dynamic, so that we can take any length of array and any length of vector and any number of processes, we'll have to write a slightly more complicated code, which we will not discuss here. I will leave it as an exercise to the programmers. So now let us go back to the presentation and see what actually happened over here. So what essentially is happening is that we initialize, the root process initializes the vector, which is 1, 2, 3, 4 up to 8. The MPI scatter takes each segment of this vector V and gives it to each process. There are 4 processes. Each process then computes the partial sum of its assigned elements. Each process shares its partial sum with all the processes. The root computes the norm and broadcasts it using MPI broadcast. The normalization then continues parallelly, each individual process computing its normalization of its component, and then MPI gather gets the fully normalized vector back to the root. So this completes the MPI scatter, all gather and MPI gather functionality. In an all-to-all computation, what we are essentially doing is that we are trying to take what is effectively a transpose of a matrix. If you look at the way data is stored in the 4 processes, P0 has an array from A0 to A3, P1 has an array from B0 to P3, so on and so forth. Each of them have unique data members. Once the all-to-all communication is done, we are essentially swapping data between the 4 processes. P0 will now get the first element from P1 and send its second element to P1. P0 will now get the first element from P2 and send its third element, or rather the second element, to P2. And so on with P3, it will take the first element from P3 and give its last element to P3. P1 will now receive all the second elements from each of the other processes and give out its first, third and fourth elements. P2 will be doing something similar. The graphical representation of how the data is exchanged makes things clear. But you also realize that when you're doing an all-to-all communication, there are lots and lots of communications being done. For example, you'll have communication from P1 to P0 for this pair, B0 and B1, which are being interchanged to these new locations. So you'll have 2 pairs of communication, or rather 2 sends and 2 receives for this. Similarly, you'll have 2 sends and 2 receives for A2 and C0, A3 and D0. So P0 will now communicate with P1, P2 and P3 for these 3 elements over here. Similarly, P1 will then communicate with P0, P2, P3 for these elements A1, C1 and D1. P2 will then communicate with P0, P1 and P3 for the elements A2, P2 and D2. P3 will communicate for A3, P3 and C3. You can see that there are lots and lots of communications which are going on over here. So an all-to-all is a very heavy process. Let us see how can this be used mathematically. So the example that we have is a matrix transpose. So we use MPI all-to-all to compute the transpose of a matrix by distributing it across to multiple processes. So assume that you have a mathematical problem and you have the simple 4x4 matrix over here, where the elements of this matrix are initialized as, in the first row you have 1, 2, 3, 4, second row 5, 6, 7, 8, third row 9, 10, 11, 12, and the fourth row 13, 14, 15, 16. The transpose of the matrix looks something like this, where the first column now becomes 1, 2, 3, 4, the second column 5, 6, 7, 8, the third column 9, 10, 11, 12, and the fourth column 13, 14, 15, and 16. So essentially what's going to happen is that we are going to exchange the columns and rows amongst in this matrix, and MPI all-to-all helps us over here. So now let us look at how this code is set up. So again, we have defined the matrix size to be 4 by 4 for simplicity's sake. We have the rank and size, we have a send buffer, we have a receive buffer. We initialize the matrix over here with all its elements. It's a two-dimensional matrix n by n. And we now need to have a transpose matrix n comma n, which is uninitialized and which needs to be computed. Since we have hard-coded this to be 4 processes, we have put in an additional check over here in this case, and we say that, okay, with this program requires 4 number of processes in case the number of processes that gets initialized during the execution of the program is different. We find out the rank and size of what the arguments have been passed over here. Now each process gets one row of the matrix, and then we need to figure out what the send buffer is. So we put the send buffer to be matrix rank I, and then we do a MPI all-to-all exchange of this send buffer, and we store this send buffer to this transposed matrix over here. So we then have to go and synchronize before we print it. We do an MPI barrier, and then we will then do print out the transpose matrix. If my rank is I will then print out which part of the matrix that I have. So you can just say process 1 received the information from different processes and what those processes are. In this case, remember, every process is receiving information from every other process. In the previous examples, we had a master process which was sort of receiving all the information and doing a sort of a global print. But in this case, since we are transposing information, every process is receiving different bits of information, and we want to show that out. And finally, we have another synchronization over here before we finalize and leave the code. So when we do this all-to-all, you see what really happens is that we figure out which part of the matrix each process has to send and where does it need to send it to by doing this all-to-all. So we then transpose the matrix over here essentially, and then we go and print out what each of these rows are. So let's see how this has worked. We say MPI CC minus standard is equal to C99 transpose and we create the output over here. Now we run MPI run. Let's put an incorrect number of processes. Code will immediately exit saying that this program requires 4 processes. So now let's put the correct number of processes. So remember that we had process 0 which had 0, 1, 2, 3. Process 1 had all the subsequent elements, so on and so forth. So now we run it with 4 processes, and you can see process 0 received 1, 5, 9, 13. That becomes the new first row. Process 1 received 2, 6, 10, 14. Process 2 has 3, 7, 11 and 15. Process 3 has 4, 8, 12 and 16. This is the transpose of the initial matrix, which would have been 1, 2, 3, 4 in process 0, so on and so forth. So this is how we use an MPI all-to-all communication using the transpose. Now if we go back, how do we explain this? So when we initialize, each process gets only one row of the matrix. When we do an MPI all-to-all, each process sends one element of its row to each of the other processes. Each process receives one element of the row from each row, and then the received elements now form columns of the transport matrix. And then each individual process in this case is printing the received data. Thank you.